Welcome to the course Excelling with Mathematical Modeling. Today we will be learning about the combat models. So what is a combat? So in the time of war, when two enemies face each other, there are various strategies by which they fight with one another. One of them is while taking them down facing one to one, and that particular kind is called the conventional combat model. So here we will be learning today about this conventional combat technique. The person who is responsible for this mathematical model is W. Lanchester, F.W. Lanchester. He is a British engineer and he used this modeling technique during the First World War. So he developed a model where which can be used to predict the outcome and the surviving of how many soldiers during the battle that can be calculated or that can be predicted. So that model helped in better planning, prediction of the battles and their possible outcomes. Also, that model can be manipulated to some other areas like this guerrilla war tactics, which we will be discussing, then a combination of guerrilla army or a conventional army. So today our discussion will be on only this conventional combat model. So what is this conventional combat model? Before that, so Lanchester used this simple technique, that is, the rate of change should be the rate in and minus the rate out. So the idea is that if your model can be simple and can capture all the dynamics, why make it complicated? So it is a very simple equation that the rate of change will be the rate in and the rate out, the difference between them, where this rate in means that the total number of troops that has been supplied, which we called reinforcement, and rate out is the number of troops not available for the fight. So either they are dead or they are sick or injured, that they cannot participate in the battle. So just how many soldiers have been supplied and how many soldiers cannot take part. Their difference is the rate of change. So in this combat model, which is a conventional one, so the two opposite armies, they directly interact with one another. So as you can see that they use either knives or you can use guns and sometimes even hand to hand combat. And that will not include any kind of bombing or chemical weapons or nuclear weapons or fighting with each another with guns from long range. That is not permissible. The combat is that, okay, you have to face your enemy one to one and fight with them. So if your xt and yt, they denote the number of troops, or in another word, combatants, that is the persons who are fighting with each another. This is for army A, that is xt, and army B, this is the yt. So total number of troops. Now we have to make the assumptions. The very first assumption is that the operation losses are neglected. That is number one assumption. There is no new supply of troops. That is, once there is an xt number of troops available for a certain army A, there won't be any addition of troops. Okay. So that is your no reinforcement. And number three, the most important one, the combat loss rate of the conventional army A is proportional to the size of the opposing army B. So if your xt is your number of troops for army A, the rate of change, so their loss must be proportional to the army B, and since it is a loss, dx dt must be equal to some alpha times y. So y is the number of troops for the army B, alpha is their fighting technique, and with that technique how much troops of army A they are able to kill, or they are able to take down, or they are able to injure, that depends on this alpha, their fighting skills. And since it is a loss, this is a negative sign. The same thing will happen for army B. So, dy dt is going to be equal to minus some beta times x, where this beta is the rate of the fighting skill for this for the troop of army A, and with that skill how much loss they can impose on army B, that is determined by this equation. So, if we now look into the model, it is dx dt equal to minus alpha y and dy dt equal to minus beta x. Xt and yt is the number of troops, x for army A and y for army B, and this alpha and beta, which are both positive, they are the fighting skills, or we say fighting effectiveness coefficients of the army B. So, this is for the army B and this is for the army A. There should be some initial troops for both sides, that is the initial started with x0 and army B started with some by 0 at time t equal to 0. So, now we have to solve this differential equation, and let us see what is the conclusion you get from here. So, we start with dx dt equal to minus alpha times y. You differentiate this one more time and you get minus alpha times dy dt minus alpha times dy dt is minus beta x. So, you get d2x dt square minus alpha beta times x equal to 0. And as you know, this is a second order homogeneous differential equation, and you take x equal to some a e to the power mt to be the trial solution. You substitute it here and you get dx dt equal to am e to the power mt d2x dt square equal to am square e to the power mt. You substitute them in this equation and you will get am square e to the power mt minus alpha beta times x equal to 0. So, here you have to consider a not equal to 0. So, you take a e to the power mt common and m square minus alpha beta equal to 0. Since a not equal to 0 and there is no value of m for which e to the power mt equal to 0, the only possibility is m square minus alpha beta equal to 0. And this implies m equal to plus minus square root of alpha beta, where both alpha and beta are positive. So, now your solution is going to be x equal to some a1 times e to the power alpha beta into t plus a2 times e to the power minus root alpha beta into t. Now, the initial conditions are given. I have to find the values of a1 and a2. So, you have calculated xt equal to a1 times e to the power root of alpha beta times t plus a2 times e to the power minus root alpha beta by t. I just differentiate it once, then I get root alpha beta a1 e to the power root alpha beta times t minus root alpha beta a2 times e to the power minus root alpha beta times t. So, the reason I have to differentiate it because there are two arbitrary constants a1 and a2 and I need two equations. So, now you have the equation dx dt which is x dash t equal to minus yt and dy dt equal to y dash t equal to minus beta xt. So, if I now put t equal to 0 here, so I get x 0, which is equal to a1 plus a2, because this becomes 1, this also becomes 1, and it is given that x 0 is x 0 and y at the time t equal to 0 is y 0. So, this value is x 0. And if I write x dash 0, so I get root alpha beta a1 minus a2, that is equal to. Now, this I have to find from here. You have x dash t equal to minus alpha y t. So, x dash 0 will be minus alpha times y 0. And what is this y 0? It is minus alpha times y 0. So, your x dash 0 is minus alpha times y 0. In the similar manner, y dash 0 is minus beta times x 0. But here I will need only x dash 0, so I will be using this particular value. So, this is minus alpha times y 0. So, gives me a1 minus a2 equal to minus alpha times root alpha beta y 0, which is minus alpha by beta y 0. So, I have this equation, say 1, and I have this equation, say 2. So, I just solve for a1 and a2 from 1 and 2. So, if I just add them, 2a1, that is equal to x 0 minus root of alpha by beta y 0, which implies a1 is half of x 0 minus root of alpha by beta y 0. And if I just subtract them, 2a2 is equal to x 0 plus root of alpha by beta y 0, which implies, sorry, this is a2 equal to half of x 0 plus root of y by beta y 0. So, I will substitute this a1 and a2 in this x, and I get my x t equal to a1, which is equal to half of x 0 minus root of alpha by beta into y 0 into e to the power root alpha beta times t plus half of x 0 plus root alpha by beta into y 0 into e to the power minus root alpha beta into t. So, that is the solution of x, and in the similar manner I can calculate y t, which will be half of. So, there are two ways of calculating this y t. Either you have to do this whole solution, or y t can be calculated directly from here. That is, your y t is x dash t equal to minus alpha times y t. So, y t is minus 1 by alpha x dash t. So, you just have to differentiate this and divide by alpha to get this y t. And if you do that, you will get this to be equal to beta by alpha minus x 0 minus root of alpha by beta y 0 e to the power root alpha beta t plus x 0 plus root of y by beta y 0 e to the power minus root alpha beta by t. So, basically I have this equation for x t and I have this equation for y t. So, now from these two equations I will try to give you the conclusion of what is the outcome of this compact model. So, please note that this is a positive one, but this one will give you a variable answer as I can say the condition that if x0 is greater than this, I will get one thing. If it is less than 0, I will get another thing. If it is equal to 0, I may get any other solution. So let's check that. So the very first thing is when your x0 minus root alpha by beta y0 is greater than 0. So I already give you the solution here. So this particular thing has been taken greater than 0. So if this is greater than 0, then from here what we can see is this whole thing is positive. E to the power minus root alpha beta t is always positive. This thing is positive, and e to the power root alpha beta t is positive. So xt is always positive. So if your x0 minus root alpha by beta y0 is greater than 0, then it is clear from this particular equation, say 3, and this equation, say 4, implies xt is always greater than 0 for all t greater or equal to 0. So even if you put t equal to 0, you will get the value is coming to be x0, which is your initial value, and that is also a positive quantity. So xt is always positive when your x0 minus root alpha by beta y0 is greater than 0. Now either your yt will be positive or yt will go to 0. So suppose I assume, say, yt is equal to 0 for some time t equal to capital T. So let us see what is that capital T here. So I will substitute this value here, and I will get half of root of beta by alpha into minus x0 minus root of alpha by beta into y0 e to the power root of alpha beta capital T plus, sorry, this half won't be there, x0 plus root of alpha by beta into y0 into e to the power minus root alpha beta times capital T, and this value is equal to 0 for some value capital T. So this will imply that this is a non-zero quantity. So it will imply that x0 plus root of alpha by beta y0 into e to the power minus root alpha beta times t is equal to x0 minus root alpha by beta y0 e to the power root of alpha beta times t. So basically what I have done is that this particular thing is equal to 0, and I have taken this to the right hand side. And once you do that, you just divide, because I have to calculate this capital T. So x0 plus root alpha by beta y0 divided by x0 minus root alpha by beta y0 is equal to e to the power root alpha beta capital T by e to the power minus root alpha beta capital T. This goes up, e to the power 2 times root alpha beta capital T. And you take log on both sides, and you can calculate ln divided by alpha by beta y0, and this will give you 2 root alpha beta times t, and hence your t is equal to 1 by 2 root alpha beta and ln times x0 plus root alpha by beta y0 divided by x0 minus root alpha by beta y0. So we get a positive time because this value is positive, for which the value of yt can be equal to 0. So the conclusion is that your xt is always positive no matter what the value of t is. So your xt, this is always positive no matter what the value of t is, and your yt it gives a finite capital T for which your yt is 0. So, the troops of army B become 0 in some finite time, whereas the troop for army A is still positive. So, army A wins the battle. Once again, you have calculated, you have shown that this xt is always positive because this particular expression is always positive, and if this particular expression is always positive, then this is positive, this is surely positive, exponential values are always positive. So, xt is always positive. Then what you have shown is that let us see if you can find any finite time for which this yt is equal to 0, because xt is always positive, and you have shown that okay, there exists a capital T which is finite and your yt becomes 0. So, yt means the troops of army B become 0 and hence army A wins the battle. So, that is the case if your x0 minus root alpha by beta y0 is positive. Now, if you want to see the numerical value, this is what you will get. So, this is your alpha and that is your beta. Yeah, so this is your alpha and this is your beta. So, alpha is 0.3 and beta is 0.4. We have taken both the initial values of the army to be 500. So, it starts from this. So, I have prolonged this curve, but actually it will stop somewhere here. This is your army A, this is your army B. So, as we have shown that the number of troops for army B will be 0 at some finite time. So, this is that finite time for which your army B becomes 0 and your army A still have this positive number, and you can see that it is growing. So, the numerical value confirms that this particular value x0 minus root of alpha by beta y0 is 66.99, which is positive, and hence the numerical result confirms the analytical results. Let us take the second case. So, in the second case we take that when x0 minus root alpha by beta y0 is less than 0. So, then what happens? So, if this is less than 0, then from here you see that this is less than 0, and with this negative sign this whole thing becomes positive. So, this whole expression along with this negative sign becomes a positive quantity. This is also a positive quantity. This is again a positive quantity. This is again a positive quantity. So, in this particular case, if we write this as 5 and this as 6, so from 6, yt is always greater than 0 for all t greater or equal to 0. Again, you can check, if you put t equal to 0, you are getting finite value of this quantity, which will be y0. So, now let us, with the same logic, let us come to xt. So, we say that this is now a negative quantity, this is a positive. So, I do not know whether xt will be totally positive or it may go to 0. So, let us assume that there exists a time t1, a finite time t1, for which this xt1 vanishes, and I will put half of x0 minus root alpha by beta y0 into e to the power root alpha beta times t1 plus half of x0 plus root of alpha by beta y0 into e to the power minus root alpha beta times t1 equal to 0. So, please note that this is a negative quantity. So, when I calculate this t1 in the similar manner, I will get t1 is equal to 1 by 2 times root of alpha beta ln x0 plus root alpha by beta y0 by x0 minus root alpha by beta y0 with a negative sign. Now, this quantity is negative, and along with this negative sign, this whole quantity is positive. So, inside the root nothing is negative, this is also positive, this is also positive. So, you get a finite time t1 for which your yt is equal to, for which your xt is equal to 0, and hence in this case you have army B wins. And if you see the numerical result, so this is again alpha and this is beta. So, in this particular case again it reaches 0 somewhere at this point. So, this is for army A and this is for army B. So, army A becomes 0, the number of troops xt at some finite time, and your army B is still positive, and hence your army B wins. And in this particular case x0 minus root of alpha by beta y0 is a negative quantity, and again the numerical result supports the analytical calculations or findings. And let us consider the third case where your x0 minus root of alpha by beta y0 is equal to 0. So, if it equals to 0, then from here what happens? Then this one vanishes, this one vanishes. So, what you get? You get your xt equal to half of x0 plus root of alpha by beta y0 e to the power minus root alpha beta times t. And from here again this becomes 0. So, you get this is equal to, sorry, this half will not come. So, half of root beta by alpha x0 plus root of alpha by beta y0 into e to the power minus root alpha beta times t. This is your yt. So, from here you can see that if your t becomes large, then this value goes to 0, this value also goes to 0. So, when your t becomes large, both your xt and yt equals to 0. But if I divide xt by yt, so this whole thing get cancelled and you are left with root of alpha by beta, which is a constant. So, conclusion is the ratio between the number of troops of the two armies in battle remains constant in time. So, basically the kind of damage that one army produces to the other, they remain some sort of constant. If you take the ratio of both the troops, they gives you a constant value, and if that is the case, then and over time it becomes 0. So, if that is the case, it is called that this is a case of tie, this is the case of tie or draw. So, none of the army wins, and at the end in infinite time both the army, the number of troops dies, they become 0. If you see the numerical, it is also giving the same thing, that over time it starts with 500, over time this army A goes to 0, over time this army B also goes to 0. So, this is about this conventional combat model. In my next lecture, we will be talking about another type of combat model, which is a gorilla type combat model. Till then, bye bye.